Remember the last scene of Interstellar, where we see Cooper, who is 35, reunite with his daughter, who is 99, after completing his space mission? This can be explained by a simple phenomenon called time dilation, which is a manifestation of special relativity. The word relative means dependent on relative motion between frames of reference. Let us consider a spaceship A moving with the velocity of 0.5 c with respect to spaceship B, and we switch on a light on spaceship A. From c, we mean the speed of light. Now the light is expected to travel at a speed of 1.5 c with respect to B, but velocity of light remains constant in all reference frames. This happens because an observer on A will not measure time the same way as an observer on B will. On A, time will move slower as compared to time on B, and its length will be shorter than that of B, which is why time dilation is also known as length contraction. Combining all these relativistic factors, the value of the speed of light remains same. Thus, if velocity of light remains same for both the observers and the space-time measurements change, we have the phenomenon of time dilation. Special relativity deals with observers in constant relative motion. The cases of accelerated relative motion takes into account the theory of general relativity. I now take you to an animation of an experiment to demonstrate that a freely falling body does not feel the effect of gravity. The animation is extended to prove that the body actually experiences no gravity in its own reference frame. The apparatus has a pair of metal contacts and an elastic string on which we put a ball. Because of the weight of the ball, the contact breaks and the LED stops glowing. Hence, with no force on the string, the light glows and it stops glowing whenever there is some force. Now, we drop this apparatus from the top of a building. We observe that the LED glows during free fall. According to Newtonian physics, gravity is an innate property of matter to attract matter towards itself. In Einstein's theory of general relativity, gravity is a distortion of space-time. Particles follow straightest paths in space-time. But because space-time is now distorted, even on the straightest paths, particles look accelerated, as if they were under the influence of what Newton called the gravitational force. If we do a similar experiment for a body with constant acceleration in the opposite direction, the object gains weight. Thus, effects due to gravity can be mimicked by effects due to a uniformly accelerating framework. Let us think of a dark accelerating elevator and a ray of light entering it. The path of the ray of light will be curved. Now, if there is no acceleration but only gravity, the path of light ray will still be curved. Assume this piece of cloth to be a grid depicting space-time. The big ball is the sun and the small one is the earth. Due to the curvature caused in space-time because of the massiveness of the sun, earth revolves around it. Hence, space-time in presence of gravity is curved. Space-time is absolute in special relativity, but it is a dynamic entity in general relativity. It can be distorted by matter, and these distortions govern the motion of matter.
Screens.
Wasn't that cool?
us. Unfortunately for us, we're not able to experience what Cooper experienced while entering the black hole. Black holes are created when a massive star dies, leaving behind a massive amount of matter concentrated in a small area. Not even light can escape its gravity. If we get stuck in a black hole, our death will be instantaneous. But I can assure you that what we experience before dying will be phenomenal. We would be pulled by the gravitational tides and get spaghettified. Our entity will be crushed into infinite density and no signs of our existence will remain. From the reference frame of a distant observer, time would get slowed down as we approach the black hole, and it will stop as we reach the gravitational radius. Cool, huh? The existence of black hole is one of the major predictions of general relativity.